Hello, everybody. It's nice to welcome you here. I'm very happy that so many young people arrived, yes. And we are starting, hello? We are starting today. My name is Aleksander Byrski. I work at the Faculty of Computer Science. And welcome to the first part of the seminar of nature-inspired computing methods. And today we have the honor of welcoming Professor Ghazali Talbi from University of Lille, from France. Yes, Professor Talbi is a renowned researcher in the area of meta-heuristics and is the author of one of the first comprehensive monographs of meta-heuristics. Yes, so thank you for coming, and let us start with listening to Professor Talbi, and then we'll have time for some questions. We have also participants online, and if anybody online would like to ask some questions, of course, it will be possible to realize that. So, Professor Talbi, you have the floor.
So first, thanks, Alexander, for the invitation, and thanks for you to be here. So I'm happy to be here in Krakow and the AGS at the university, and I will give you a talk on my recent research related to neuromorphic-based optimization. So this is a new discipline. There are very, very few papers in this area. So I will convince you that neuromorphic-based optimization will be very important for the future. So before introducing this talk, let's give you an overview about what I did in the past. So as you see here, I started research a long time ago. The priorities of my research was, of course, meta-heuristics, computational intelligence, and also high-performance computing. So from the beginning, I create my team. Then the name of my research team was parallel and cooperative optimization. So optimization is important, and the cooperative part, mimetic, hybrid part is also very important. And also we have always in mind a very efficient implementation, because this is very important for many problems in terms of design and in terms of implementation. Then, of course, I switched to, this is incremental evolution, to multi-objective optimization, how to design hybrid meta-heuristics with mathematical programming, with constraint programming, then how we integrate machine learning for optimization and optimization for machine learning. And we design some very interesting approach to solve problem, which is named fractal large-scale optimization. And the idea here is how to design massively parallel algorithm that solve very complex problem, very expensive problem, very large-scale problem using the fractals. 5 years ago, we switched to solve a very expensive optimization problem. So, for instance, in machine learning, those problems are very popular. Hyperparameter optimization of deep neural network, neural architecture search of deep neural network, and spiking neural networks. And those problems are very complex to solve because the objective function is very, very expensive. It takes minutes, hours, and days just to evaluate one solution. So you have to design some Bayesian optimization technique to solve such problem. And those are, of course, very, very important and high impact problems. Everything now is related to AI, deep learning, so you have to optimize the model. And if you would like to optimize the model of deep learning, you have to optimize the hyperparameters, you have to optimize the architecture of the neural network model, etc. And then, now in France, as in any country, there are two high priorities in research, two big projects. The first one is dealing with what we call exascale optimization. So the new architecture, HPC architectures will be exascale. So you will have two exascale machines in Europe. One will be in France and other one in Germany. The German one is already operational. The French one in 3-6 months will be operational. So the idea here is how to design exascale algorithms that go to solve the problem efficiently. So we are dealing with this kind of algorithms and to try to design them, to develop them on exascale machine. And then 2 years ago, working on spiking neural networks, this is the next generation of neural network, okay, which are more biologically plausible. And then I asked myself, why do not use spiking neural network to design optimization algorithms? So this is the idea, and this is the objective of my talk. I will convince you that this model of spiking neural networks, of neuromorphic optimization, can be used to design new algorithms to solve problems, okay? So, motivation. What are the motivation of this work? Of course, I'm here to solve large-scale and complex problems. We are not here to solve toy problems. So more and more problems in practice are large-scale. You have huge number of decision variables. You have very expensive objective function. You have hard constraints to satisfy, etc. For instance, I give you 2 examples. Training deep neural network, very complex problem. Fine-tuning LLMs, very complex problem. Huge number of variables, very expensive objective function, a lot of constraints, etc. And of course, if you are from energy, system, engineering design, logistics, biomedical, everywhere you have large-scale optimization problems, okay? And the second motivation, what about problem arising in embedded systems and edge computing IoT, which require low power, low latency, and small hardware footprint. So this is important in embedded system and edge computing, IoT, where you have many problems to solve, and you have to be careful about what is the energy that you would consume, what is the latency that you will have, and the hardware footprint of your algorithm. So this is a very important issue in many problems. Okay? So all your machines today are inspired by the Turing machine, the von Neumann machine. So the problem of digital, classical von Neumann architecture, which are based on clock-driven architectures. And as you know, this is the end of this kind of architectures. We cannot, this kind of architecture, because of the Dennard scaling, the Moore law, and the limited bandwidth between CPU and memory, this is, let's say, the end of the story of von Neumann machine. We have to switch to other computing paradigm. Why? First, higher energy consumption. The energy consumption in this kind of machine is very, very high because of the bandwidth between CPU and memory. Okay? The increased latency and larger hardware footprint. I don't know if you have some ideas about the environmental and economic impasses in these architectures. Just AI electricity consumption in about 2030 will be 20% of global electricity consumption. So this is crazy, okay? And this is a very important aspect to take into account. So for instance, I give you just one example. If you just training a single model like GPT-3 produce, look, the numbers, more than 200 tons of carbon. It takes more than 1,300 megawatts per hour of electricity. They are using thousands of GPUs to train the model, and it takes some months to train the model. And I didn't give you the cost of doing such things. It takes more than 200 million euros to train a model. High cost, high energy consumption, high footprint of hardware. This is an impasse. We cannot continue with those numbers. We cannot continue to develop more and more complex models. So there is a huge need for novel computing paradigm. And what are the most popular paradigms today? Of course, quantum computing and neuromorphic computing. Okay? I will talk about neuromorphic computing. Good. So what is neuromorphic computing? So it's, of course, emerging technology, and it's alternative to von Neumann. The inspiration is drawn from the human brain. Everything is inspired from the human brain, okay? For the design of new hardware and software system. Let me say that in existing work, the hardware community is much more popular in this area than the software. Many people, many researchers are coming from the hardware, okay? Software, the community is very reduced. So the next generation of computers will be analog and not digital. Your brain is analog computer, it's not digital computer. No. So the community of neuromorphic computing is very diverse, and it comprises researchers from various disciplines. Material science, what is the best material? Those are people from physics. What is the best material to implement neuromorphic computers? Neuroscience, of course, to have more knowledge about the brain, how it works, okay? Electrical engineering, designing new circuits, designing new hardware, architectures, and of course, computer science. But in computer science, most of the people try to solve only machine learning problem or cognitive problem. At least 90% of the people from computer science try to solve the same problem of machine learning, prediction, classification, clustering, etc. And I ask myself, why not to use this new paradigm to design optimization problems, not only to solve cognitive problems, okay? So there are many papers dealing with graph algorithms, with partial differential equation solving, signal processing. But from my side, I focus in this talk and in my research to design new algorithms inspired by neuromorphic computing paradigm. So this is the exercise. Good. So what is the contribution? Explore the use of neuromorphic computing for the design and implementation of neuromorphic optimization algorithms, what I will call neuro-optimizers. And of course, I will be inspired from heuristics, computational intelligence that are very efficient algorithms. So the inspiration will be from heuristics and computational intelligence, and then I will try to revisit or redevelop those algorithms in neuromorphic computing way. And of course, the objective is to integrate those software into hardware to achieve brain-like efficiency. I forgot to mention that your brain, your brain is, how many watts your brain is consuming? 20 watts, you know. Just one GPUs, like consume more than 300 watts. And the supercomputers today, they are consuming megawatts, gigawatts. And your brain is consuming 20 watts. Good. So the objective is to design generic and scalable neuro-optimizers inspired from evolutionary algorithms for swarm intelligence algorithms. If you would like to have more technical, so those are the first paper that I published. Of course, this is a very recent research, and then I put it on archive, so everything is available in archive. For instance, this paper, I finalized a, let's say, survey or like existing work related to neuromorphic-based heuristics. Recently, we developed neuromorphic evolutionary algorithms. We have also a general framework for neuromorphic optimization, and we submit those papers. All those papers are available in archive, and of course, we submit this paper in very well-known journals. So this is where I'm coming from. I start to 4 years of work. This is my PhD, one of my PhD students. We start to optimize spiking neural networks. What is the best spiking neural networks to solve machine learning problems? And then I ask myself, why do not use those spiking neural networks to design optimization algorithms? Good. So what is the outline of our presentation? Very quickly, I will give you the main concept. mainly neuromorphic computing, which is, I think, it's not very popular. And then very few words about meta-heuristics and optimization problems. And then I will give you some use cases in terms of design, in terms of simulation, in terms of implementation, something which is very important in neuromorphic computing. The software is the hardware. The software is the hardware. There's no difference between the software and hardware. What you are developing will be implemented exactly on the hardware. You cannot separate the software and the hardware. It's not like classical computer science, in which in the hardware you have 10 or 100 levels in software programming. Here, the software will be the hardware. And then I don't think that I have time to enter the details, but we have two case studies, neuromorphic evolution algorithms and neuromorphic swarm intelligence optimization. And conclusions. So, in digital computing, you are manipulating bits, 0, 1. This is digital computers. The brain is analog, is not digital. So even the neural networks that you are using, that the second generation of neural networks, those are digital, and they are far from the brain. The biological or the brain is manipulating what we call spikes. Spikes, your brain is electrical circuits. Your brain is an electrical circuit that manipulates spikes, and the spikes are like short voltages that are transmitted between neurons. Okay, so your brain is an analog computer. Okay, so how many neurons you have? You have billions of neurons, 100 billions of neurons, and you have trillions of synapses. As I told you, the brain requires 20 watts. A single GPU requires 500 watts, and the supercomputing some megawatts. Just one supercomputing is more than 7,000 home consumption of electricity. And if you take the clouds, Google clouds or Amazon clouds, the consumption, energy consumption is more than huge cities like California. Just one cloud. So, the model behind this neuromorphic computing is spiking neural networks. So what is the main difference between spiking neural networks, which are more biologically plausible than the neural networks that you learn in university? So spiking neural networks represent the main algorithmic paradigm for neuromorphic computing, and the neurons communicate only by spikes, nothing else. Okay? So a neuron receives some spikes, and then you have some neuron model to define what will be the output according to the input. So this is the third generation of neural networks. So the program will be how I will define the structure of the spiking neural networks and its parameters. Those are biologically plausible models. So the network here will use only spike to encode the information, nothing else. So it's analog computer. Okay. And the difference will be which neuron models I will use, which synapse model I will use, which architecture I will use, which local learning rule I will use. Okay? So spiking neural networks, at the input you will have a set of spikes, and the output you will have a set of spikes. Nothing else. And you will ask me, why? I will ask you, why this architecture will consume very small energy? Why your brain is consuming very few energy? Because it's not clock-driven. It's event-driven. If I don't receive spikes, zero consumption. I do nothing. Okay? So it's event-driven, and you have billions of neurons, but at a given time, only few neurons are working. Not all. In your digital architecture is clock-driven. If nothing happened, I am working. It's clock-driven. Here, it's event-driven. It's massively parallelism, of course. Billions of workers. And this is very important. The memory is collocated with the processor, because most of the energy you are consuming in digital computers is spent in cooperating between CPU and memory, not in the ALU, okay? The scalability is native. It's asynchronous also, event-driven and asynchronous. It's not synchronous and clock-driven. The network is sparse. Every small element are communicating, small number of neurons are communicating, and the hardware, the chips today we have is 1 millimeter. 1 millimeter, okay? And you have stochasticity and you have KO, and as you know, most of the optimization algorithms you are using are stochastic. And your brain, the neural model are all stochastic or chaotic models. And of course, local learning. There is no gradient. There is no backpropagation. Everything is local. I'm learning only with local learning rules. Nothing is global. In gradient or in backpropagation, you have global learning. This is not efficient. So here, everything is local learning, and of course, it's robust to noise and fault tolerance. So this is why neuromorphic computers will consume very few power, and they can scale billions or trillions of neurons. Good. So I guess you are popular with meta-heuristics, with computational intelligence. Let's say, in some words, what are the main classical popular algorithms? You have, of course, those greedy optimization algorithms, which are constructive algorithms. And you have those iterative, where I will classify like local search-based, single solution-based. Here you will evolve single solution like gradient, like simulated annealing, like taboo search. And you have this population-based computational intelligence algorithms. And the most popular ones are, of course, evolutionary algorithms and particular swarm optimization. Okay? But forget about those names. What are the most important questions here? The most important question is how you will encode your solution, how you will define your search space. Okay? Second, what will be the variation operators that you will define? For instance, neighborhood in local search. For instance, mutation crossover in evolution algorithms. For instance, velocity update in PSO, etc. Those are the most important questions. Okay? And of course, Alexander present my book. So this is book 229. Why I spend a lot of time to write this book? I write this book not to have another book. I write this book to unify this world of meta-heuristics and focus on the important question. Okay? Focus on what are the most important questions in designing meta-heuristics. And forget about the metaphor, you know. The metaphor is good just to have an intuition to present an algorithms, but you have to focus on the important questions. Good. What are the different families of optimization problems? Of course, binary optimization problems. The most popular is QUBO, knapsack, satisfiability problems, discrete optimization problems, integer, like CSP, or permutation-based, like TSP, and of course, continuous optimization problem. And here you have a lot of well-known benchmarks to evaluate, to compare, etc. So those are a picture of the most popular problem that you have to solve to validate what you are designing. Good. Now, of course, if you are using neuromorphic computing, means that you will minimize the energy, you will scale, you will reduce the hardware footprint, you will reduce the latency. But more than that, if you design, so we are modeling spiking neural network like Markov chains. Okay, so here a program will be a spiking neural network. Okay, then Turing machine. So the distribution of this Markov chain will be my analog program. Okay, and I will guide the SNN to perform specific type of computation. So me here, I will try to define SNN that converge towards good solution to solve the problem. So the benefits are also efficient data access, scalability, parallel evaluation of the objective function, parallel generation of solution, and parallel selection and replacement of solution. Everything is done natively, intrinsically in parallel and in a distributed way. So you imagine all the operation of optimization algorithms will be done in parallel, in native way. Okay? Good. What are the most important questions? When you are designing analog program or spiking neural network or neuro-optimizer, I will focus here on neuro-optimizer, design on neuro-optimizer, you have to answer those 4 questions. What is your neural model? What is your information encoding? What is your spiking architecture? And what are the learning rules? So if you answer those questions, you have designed neuromorphic program. Good, so I will give you some answers, okay? I will give you, excuse me. So I will try to give you some answers related to those 4 questions. What's about the neural models? You know, here, there are people working in this area are mainly neuroscientists. So they are designing neural models that are biologically plausible, okay? So, for instance, there are different models, and I will compare them according to different criteria, okay? If you would like to take the most plausible model, it's the Hodgkin-Huxley. This is Nobel Prize in 1963. It's not last year. Huh? 1963, those guys have the Nobel Prize in terms of designing a neural model which is biologically plausible. But the problem with this model, it's computationally expensive. So nowadays, I will not use it because it's a very expensive model. Those are more than 4 differential equations to solve. Okay? Perhaps in the future, if we have more efficient hardware, I can use those biologically plausible models. But in the literature, you have other models which are biologically inspired, like the integrate and fire model, like the Iskevich model. So those models will offer a good balance between biological plausibility and computational efficiency. So at this time, all my algorithms will be inspired by those models. I will use the Leakey integrate and fire model, and I will use Iskevich models, okay? So to give you an idea how it works, I don't know, how it works. So suppose that you have a neuron here, spiking neuron. So at the input, you have spikes. And the output, here you will accumulate the voltage. And when the accumulated voltage is more than this threshold, I will spike. So this is the internal functioning of your model, of your neuron. It's like an electric circuit. You accumulate input spikes, and when it will be more than a given threshold, I will send the spike out to other neurons. So, of course, as I told you, biologically plausible models are computationally expensive, so they are not effective, at least today, to design neuro-optimizers. So we will use simplified biologically inspired models like LIF, which achieve low computation cost and low power, and most of the hardware we have today, they implement those models, okay? So I have to take into account which hardware is available. And I brought here the biological plausibility and the computational cost of the different, those are the most popular neural models, okay? Most biologically plausible models, and those are biologically inspired model, and the good compromise here is the LIF model or the Iskevich model, okay? And of course, don't forget this stochastic aspect, okay? Stochasticity in optimization is very important, so you have to use stochastic neural models that will add some noise and stochasticity in the behavior of algorithms. Good, now, what's about information encoding? How you will encode your information? You will manipulate binary vectors, you will manipulate continuous values, you will manipulate permutation, you will manipulate integers. How you will encode your information? Because the only thing you have is spikes. So how you will use spikes to encode information? And in your brain is using rate coding and temporal coding. So everything here is inspired from the brain, okay? So what is rate coding? So the rate coding will use the frequency of the spikes to encode the information. For instance, here you have a window, you receive 6 spikes, so you encode the information with the frequency of spikes. And you have another temporal coding, which is temporal coding like TFFS. TFFS is the time to first spike. The time to first spike will encode the information. And it depends on the part of your brain. Some part of your brain are using rate encoding, other part of your brain are using temporal coding. And time encoding, the easy, is you will encode the information using the interspike interval. So as you see here, there are different encoding schemes, and you have to select the most suited one to the problem you will solve. For instance, to my point of view, if you are solving binary problem, just take the rate encoding. If you are solving timing problem or permutation problem, it's preferable to use time encoding because time is important in scheduling problems, in permutation problems. But if you have binary problems, just use simple rate encoding. So the encoding of information will depend on the target optimization problem you are solving and which information you are manipulating to generate solution, etc. So I will not go to details, but of course, the advantage of rate encoding is straightforward implementation, robustness to noise, but the rate encoding has higher latency than time encoding. Time encoding enhances the information capacity to tackle large-scale optimization problem, and you can use also some population encoding, where the information is represented by a group of neurons rather than a single neuron, and in the brain, some neurons are using mixed of rate and temporal encoding. So this is just the beginning of the story, yeah? But of course, those questions are open questions. What are the best encoding for designing algorithms, for solving problems? But everything is inspired by the brain. So all the answers I'm using here are already have been validated by neuroscientists. I'm not inventing anything here, okay? I'm really using the knowledge from neuroscientists. Good, and what's about the architecture of the spiking neural network? Of course, you have some feed-forward networks. For instance, here for greedy algorithms, optimization algorithms, you have to use feed-forward. You don't need any recurrence. But for iterative heuristics or meta-heuristics, you have to use recurrent networks. What's about the space complexity? What's about the time complexity? You have to redefine what's the complexity of the algorithm, okay? So the complexity, the space complexity will be related to the complexity of the network. The time complexity, if you take feed forward, will be related to setup time, the run time, which is more or less the longest path in the graph, okay? So those questions still, of course, they need more research how we evaluate the complexity of a spiking neural network. What's about learning? As I told you, we will not use gradient. We will not use backpropagation because first I will not use the gradient because it's not the differentiable nature of spikes. I don't have the gradient, okay? And I will not use global learning. I have to use only local learning, okay? And the most popular and biologically plausible local learning rule is the Hebbian rule. This is well known in neuroscience. What is the Hebbian rule? This is the two neurons, okay? If A fires before B, we will reinforce the weight. If B fires before A, we will reduce the weight. So what the Hebbian rule, which is biologically plausible, says that the time difference between presynaptic and postsynaptic spikes determines synaptic weight change, okay? And as you see here, it's local learning rule. We don't need global information. So it's scalable, okay? And of course, In the literature, people are using some supervised learning. I don't like this kind of work. I will never use this kind of work. That conversion between ANN, SNN, do gradient, and come back to SNN. You will do some surrogate gradient to approximate the gradient. For me, this is far from biological plausibility. And what is, I start to work on this, and we have one paper that is under production. Reinforcement learning is implemented in your brain, in decision taking, in decision making. So there are well-known reinforcement learning procedures in the brain, what we call reward STDP. And what we are doing now, we are reading a lot of papers from neuroscience to implement the reinforcement learning rules of the brain in optimization algorithms. Okay. Good. I will skip. What time is it? Yeah. Wow. So now you have designed your program. What does it mean? You have designed your spiking neural network. You have an answer about those questions. Two different ways. You simulate your spiking neural network, because you know the neuromorphic hardware is not available for anyone. Okay? So, but there are a lot of simulation tools, as you see here. 10, 20 different simulation tools. So the first step is to simulate your network using those simulation tools. So I give you here the list of the most well-known. What are the criteria? User-friendly, of course, flexibility, GPU handling, hardware support, because the second step will be to implement the SNN on the hardware, okay? Biological plausibility, performance, and scalability. And as you see, those criteria are not correlated in terms of there are some, for instance, there are some simulation tools that are used only by neuroscientists. So they are more biologically plausible, but they don't take into account the performance, okay? So from my point of view, this is my point of view, currently, things can evolve because this domain is not mature, okay? This is just the beginning of the story, the beginning. So we have used Lava, which is designed by Intel. We have used Nango, which is very nice simulation framework, and PIN. So all the results I will give you are based on Lava, on Nango. I have a small preference to Nango. Why? Because Nango is also used by neuroscientists, and all answers that are biologically plausible for those 4 questions are already implemented in Nango. So I don't have to reinvent the wheel and implement all knowledge of neuroscientists. Nango is a very rich framework where you can use many answers of those questions and which are biologically plausible. Lava is an environment which is designed by Intel. I try to have some collaboration with Intel. They are in Munich, not far, I don't know how it's far from here. But even Intel, what I understood, they are not happy with Lava because it's high-level language. And as I told you, in this area, the hardware is the software. You cannot, and it's not good to be very, very high level. You have to understand. You have to design a circuit. A program is a circuit. I will design a circuit, okay? Good. What is the hardware in this area? What's about the hardware? I classify the hardware in 3 types of hardware. Of course, digital architecture, because digital, the CMOS technology is everywhere. So the cost to design a digital architecture is very low compared to analog or mixed architecture. So most of the architectures today are digital, based on CPU or ASIC or FPGA. For instance, the Spinnaker is very well known in Europe. The Louis Intel chip, this is Intel chip. For instance, this architecture is composed of 700 Louis chips and implements more than 100 million neurons, okay? And you have FPGA is very popular for the flexibility. But the future, from my point of view, currently digital world because of cost of flexibility, genericity. But the future will be analog. Future will be analog. Okay? It will take some time, but the future will be analog. And there are a lot of work in this area, but not in computer science, material science, physics, electrical engineering. Many people are working in this area. Okay? And of course, you have some mixed architecture, analog component for the neurons and synapse, and digital component for the network management, etc. For instance, brain scale, neurogrid, brain drop are examples of hybrid architectures. Good. Just an example. This is the Louis chip. This is, you see about the hardware footprint, it's 1 gram. The chip is 1 gram and 1 millimeter square. Okay? And this is the biggest machine we have today, which implements 1 billion neurons. It's a small box. And you implement 1 billion neurons. Okay? This is the future. The future, it will be analog devices like memoristic devices, optical devices, photonic. Did you make a parallel with another area here when I talk about photonic, when I talk about ferroelectric, optoelectronic? This is more or less what is happening in quantum computing area. In the hardware point of view, I'm sure that in the next decade, quantum computing and neuromorphic computing will share more or less the same hardware. And I'm working on this question. The next question I'm working on, how to combine the world of quantum computing and neuromorphic computing. This open, very nice challenges. Good. Okay. Now, I will give you 2 case studies, okay? 5 minutes before, just... I will give you 2. The first study I made, I hired one student 2 years ago and asked him, I have designed more or less the algorithm, and I asked him to implement it using the lava environment of Intel. So the first study we did is a neuromorphic evolution algorithm to solve discrete problems. Kubo, knapsack, TSP, SAT, the most popular problems. And as I told you, in 1995, I told you about parallel cooperative optimization. I have designed, in my PhD, I have designed the parallel genetic algorithms, which is today named parallel cellular algorithm. But I have designed it in 1995. I was the first one to design this algorithm. But in my PhD report, and then this model, I don't know if you are familiar with evolution algorithms and parallel cellular algorithms, cellular evolution algorithms. The idea is to map the population. The classical algorithms will map in population on complete connected graph. Here is to map the population in a given graph, for instance, torus here, or grid, and then the selection and the recombination is done only locally. We don't have to design global synchronized operators. Skip everything global, everything synchronous, forget about it. Everything must be distributed, local, asynchronous. So this model designed in 1995 is very well adapted to neuromorphic computing. I will map the graph, this graph, on a spiking neural network. Every neuron or every group of neurons will collaborate only with neighbors to do selection or combination. And then I will ask those questions. When I will exchange information, what is the topology, which information I exchange, and how I will do the replacement. So this spatially structured graph is very well suited to neuromorphic computing. So we took this model, but we have everything to reinvent. What is the neural model? What is the information encoding? What is the topology? And how you compute the evaluation function using group of neurons. So everything you have to do from scratch. So here, for instance, I give you just the network that will compute the Kubo objecting function. It's matrix vector multiplication. How to do matrix vector multiplication using spiking neural network. Okay? So if you would like to have more details, just take the papers I give you, which is available. So okay. And then we implement mimetic algorithm. Mimetic, it's a very well-known hybrid model that you combine evolution algorithms with local search. Because as you know, evolution algorithms are very efficient in exploration, but exploitation are not very efficient. So we add local search that improve the exploitation of solution. And of course, we have been, I will not say we have been surprised by the results, but I can tell you, I will be, for sure, I don't have any doubt about that, we will be competitive in terms of quality. This is not, for me, it's not the main challenge. I'm sure that in terms of quality, we will be competitive. Why we will be competitive? Because we are expert in optimization, and I am implementing things that works. So no surprise. But the issue here is not quality, it's latency, how much time you will take to solve the problem, and the energy, how much power you will use to solve the problem. Quality of solution for me will be okay. Okay? So this is the result. We compare with simulated learning, we compare with the optimal solution for Kubo, we know, and this is very good. Very quickly, this is the simulated learning, this is the neural optimizer for Kubo. Very quickly, we converge toward the optimal solution. So we are better than classical simulated learning, and for small to medium problems, we always have the optimal solution. We apply it. I will not give you this. Mimetic is, of course, no surprise. Mimetic is better than non-mimetic algorithms, and we apply it to SAT problems, which are very well-known problems. The same behavior. We implemented to knapsack the same. Knapsack is a constraint problem. You have some constraints. Kubo, you don't have constraints. And in terms of quality of solution, it works very well. Now, if you ask me what's about time, the time here will be some milliseconds. Because the neural models the timing is related to milliseconds. So all the time we have here will be some milliseconds. Some milliseconds. We never have more than 10 milliseconds to solve all those problems. And I will give you some insight about the energy in this part. Then, this is the second step. So the first is student, engineering student. We did this work in 4 or 5 months. Good. Next step, we have to go further. So I hired a postdoc, and we did more solid work. And we have already framework. GitHub, which is available in GitHub, and which implement swarm optimization algorithms. And of course, we are improving. This framework is implemented in Lava, the Intel framework, but we are switching slowly to Nengo, because what we are doing in research now, to be more inspired by the brain, by neuroscientists' work, and Nengo is much more efficient for that. I will not spend my time to implement the knowledge of neuroscientists, okay? So the idea here is the postdoc was more familiar with particle swarm. with ant colonies. So we decide, and more familiar with continuous optimization. As you know, the word of continuous and discrete is different, okay? So we go towards continuous problem. And then we have designed neuromorphic optimizer, which is very generic, and it's based on a set of agents. You have a set of agents. This is one agent, okay? You have a set of agents that implement the most important operation of an optimization algorithm, okay? Selection, generation, evaluation, okay? So we have defined multi-agent system where you can implement any optimization algorithms like PSO, evolution algorithm, ant colony, etc. So we have a paper that describes all the organization, the architecture of this framework. So this is the what we call the neuromorphic heuristic units. This is the unit, and this is the architecture of the set of agents. Okay. So we have a set of units that collaborate locally to solve a given problem. And we implement it using Lava, and I will give you some information about what's about the power consumption using the Lowy hardware. So we validate using the one-known continuous problems. So we use one-known benchmark, and we see how it scales. So we converge towards the optimal solution. As I told you, no surprise. No surprise. We are inspired by, we are doing optimization more than 25 years. We know what is working, okay? So we are inspired by the most efficient operation, okay? We're not inspired only by metaphors, okay? We are inspired by the good, efficient operations. And then we got very good results in terms of quality. But for me, the main challenge is latency, energy, and scalability. I'm here not to solve problems of millions of variables. I'm not here to solve problems of 10 variables, 50, 100. I'm here to solve problems, very, very large-scale problems. And then, as I told you, 15 milliseconds in terms of latency, no more. And energy, 10 watt on Lowy. We evaluate the energy we are using for this problem, 10 watts, using the Lowy chip. So the motivation, I hope that you are convinced that neuromorphic computing will change the landscape in solving large-scale problems and not toy problems. There are people here that have application on embedded system, on edge computing, on IoT, this is very important. If you would like tomorrow to planify or control drones, robots, telephones, watches, you need to take into account the energy. Okay? So, let's conclude. So if you would like to have more technical details, the papers are available on archive. Have a look, and if you have some questions, just send me an email. So let's conclude. Low power, low latency, small hardware footprint are very important issues. Okay? Particularly suitable for embedded system, edge devices, IoT. You don't need cloud. What is bad in cloud? Security aspect. You have to exchange data. If you deploy your problem on the cloud, you have to exchange data. So security, energy consumption, latency, bye-bye. Here, everything on the edge. Everything in the edge. Of course, this is the beginning of the story. Neuromorphic computing technology is not ready for large-scale industrial, but it's coming. This is a must. Like quantum, this is not ready at all. But 5 years, 10 years, more efficient hardware is coming. So You know, in the hardware domain, to be industrial, you need some time. Okay? But it's expected to become a major area. In the coming decade, I have no doubt about that. And of course, there will be transition from research to real-world impact, and it's already in some application, in a space application, robotics application. Okay? And of course, the perspectives. This is very nice perspective. Tackling decentralized optimization problem, co-evolutionary optimizers to, for instance, planning swarm of drones. You have a swarm of robots, you have swarm of drones, and you have decentralized problem. You don't have global problem. Okay? And other families of optimization problem, expensive problem, and of course, the same problems, such in artificial neural network. You have to optimize the parameters, you have to optimize the neural architecture search. But for me, this is my point of view, the future will be extremely heterogeneous. So you have to, our future students will have a heterogeneous architecture, digital, quantum, neuromorphic, and you have to program heterogeneous architecture. This is for sure the future, not in the next year, 10 years. You will have heterogeneous architecture. Quantum cannot do everything. Neuromorphic too, digital too. So you have to deploy your application, your program on heterogeneous architecture. So the future will be extremely heterogeneous, which will dominate the market. Even now we have heterogeneous architecture. We have quantum, we have digital supercomputers that cooperate, and you have to map your program, one part in quantum, one other part in digital, etc. So we'll finish with some publicity. Of course, this work generates a lot of challenging, innovative research. So I'm here to start some nice collaboration. So any collaboration with the laboratories or of AGS University is welcome. My point of view is there is a lot of interesting things in this area. This is the beginning. So any collaboration is welcome. And 10 years ago, I have created this conference. Why? Why I have created this conference? Optimization and learning. Because there is no bridge between optimization community and machine learning community. If you go to machine learning community, no one from optimization. And if you go to operation research optimization community, they don't know what is happening in machine learning. And I'm working on the two areas. So I decide this conference is not attracting 2,000 people, 60, 70, but it's enough for me. We are here to discuss, to exchange, okay? And every year we have this conference. So this time it will be in Greece. It's far from here, Greece, or it's okay? But you have a good airport, so you can join us. In Creta Island, this is a very nice island in Greece. So the deadline is January or December. So this is a nice event to people exchanging ideas, bridging the gap between machine learning and optimization. And the subject I present today is exactly an example. And why not in Krakow next year? Good place to organize conference. Localization, attraction, quality of life. So I will discuss with Alexander. I think Krakow will be a good place to organize. And what is nice in this conference? Medium size. So we exchange a lot between participants. We have time to discuss. I don't like the conference. Next week, I will go to San Diego, NeurIPS. You know the NeurIPS conference? 20,000 people, you know. You don't have time even to read the program. I don't have time to read the program. But it's different kind of conference. Thank you. If you have any question, I'm here to answer.
Thank you very much, Ghazali. I can only say, why not in Krakow? I don't see any objections right now. So let's talk about it, but let's first ask about asking.
Now I'm in love with Krakow, so.
Okay, that's great. Good for us. It was one of the reasons for bringing you here. Do we have questions to El Ghazali? Piotr.
Thank you very much. I'm afraid next week we'll be in love in San Diego, probably.
Yeah, okay, so we will meet there.
No. Anyway, I believe those neuromorphic devices are not universal, are not jack of all trades kind of computers, let's say.
Yes and no. Yes and no. My first slide, there is one paper that proved that it's universal in terms of Turing machine.
Are they?
Yeah. It's a universal machine. It's not non-universal.
Of
course, you are not familiar with that. To design a program, you are not designing sequence of instruction. You are designing Markov chain, okay? But theoretically speaking, there are some papers that prove that neuromorphic architecture is universal in terms of Turing machine. Is a Turing machine, universal Turing machine.
Any
so
architecture?
Theoretically, you can implement every operation.
Do you mean that any device can perform any operation, right?
Yeah, theoretically, but the exercise will be perhaps difficult.
Okay, so I don't have.
Yeah, but ask the question.
I wanted to ask you whether they are. I believe they are like algorithm-specific devices. So you need to construct another device to implement each algorithm, and I wanted to ask you whether they are problem-specific as well.
Yeah, okay. You don't. I have. I will show you. Yeah. As I told you, in terms of architecture, you have. Those are the main families of architectures, okay? You don't have to design new circuits. This is why I skipped this slide, but look, this is important. When you have designed the program is spiking neural network. Then the question is how to map this spiking neural network on a given architecture to be the most efficient. This problem is important, okay? So here you have optimal mapping of SNN on a given hardware. And if you have large-scale hardware, you will have like a hierarchical architecture of today, our hierarchical architecture. You have a chip, you have a board, you card, a board, etc. So you have a mapping problem. And you have also, what is nice in neuromorphic, those are the configurable architecture. You can even change parameters of your architectures. So there are new problems, which are very important. I don't have resources to solve those problems, but it's in my program. Once you have the spiking neural networks, how to map it on a given architecture, and how to configure the hardware, because some hardware is reconfigurable, to map to your program. So new problems, and but you will not redesign the architecture. Okay, but this is in classical architecture. But in the other area, if you are using new material like for instance those people today they are designing a new circuit for the program. But this is at the material device level. This is not at the architecture level. So there are many papers how to use ferroelectric devices to implement the shortest path in a graph. You know what is very nice in this area? The hardware is not far from the software. This makes it very efficient.
Okay, thank you very much. Do we have other questions?
Thank you. So first of all, thank you so much for your presentation. It was very informative, and I could understand almost everything, so that's nice. So
you can present yourself to have an idea. Where you present yourself, PhD, lecturer.
Okay, but do you want to go first?
Okay.
So I am Katarzyna Filus. I finished my PhD 1 year ago, and I am from Gliwice, from the Institute of Theoretical and Applied Informatics, Polish Academy of Sciences. And actually, I have 2 questions. So the first one, I wanted to ask you about this scale of the algorithms. So currently, what is the maximum size, let's say, in terms of parameters of the practically implemented architectures or neurons?
Yeah, if you are using simulation, we can go towards 1 million without any problem. But if you would like to implement on the hardware, this is another question. Because the only commercial hardware now is Spinnaker. The low-yield chip, you need to have some connection with Intel to have it. You cannot buy it. So, as I give you some numbers here, what is so Spinnaker, they create a company that sell this, the hardware based on Spinnaker. And so this is the biggest machine you have today. So you can implement 1 billion of neurons. But we expect 2030, we expect that we will implement the same number of neurons that your brain. 2030.
Yeah, sounds amazing. Yeah.
And I have no doubt about that because, implementing neurons is not GPUs. This box implements 1 billion of neurons.
That's true. So
and the people in this area are expecting in 2030 we will have 1 billion of neurons.
Yes, so a lot. So now a second question, and actually it is connected to the one because I am from this machine learning domain. You mentioned like one of the 2 things, and I deal with problems of machine learning in general, so explainability and security. And like if we in the future have a lot of parameters like this, a lot of neurons, I think that similar problems can appear. So what do you think about it? Explainability, security like adversarial attacks or something like this,
What do you mean by security?
Like, is it easy to make such a network, spike neural network, make mistakes,
Let's focus on the explainability.
Okay.
Explainability is an important issue in machine learning because you are designing models. You have to explain what your model is doing to explain the results. But here, my exercise is, I have a new computing paradigm based on spiking neural network, okay? But I am inspired by 2 important ideas. Computational intelligence, what we are doing more than 30 years, designing efficient algorithms, and neuroscience. And this is my experience on 3 years, just 3 years, 4 years. There is very interesting mapping between the 2 areas. Everything you are doing, evolution, co-evolution, reinforcement learning, all those operators are in your brain.
Yeah, analogies are everywhere.
The analogy. So I am doing just the analogy between computational science and the brain, and I'm implementing algorithms that I can explain to you. It's not like I can explain the algorithms. Okay? It's not like machine learning, where you have the model is a set of weight, complicated to explain. But here I can explain the algorithms. But with my student PhD, I start in this area with my PhD student to optimize the spiking neural network to do machine learning, computer vision, blah blah, etc. Imagine that we have the same problems. We are optimizing spiking neural network to do classification.
Yeah, and work on pixels.
I am optimizing it. I will explain nothing, just the result. But here, the idea, I can explain the algorithm and the implementation, so I don't have problems with explainability.
But do you think it will be easier or more difficult to explain, the decisions or mistakes, even more importantly?
You prepare a degree in computer science, so you are learning von Neumann architecture. You are not familiar with this new paradigm. Yeah. Quantum computing, the same. It's not easy to design a quantum computer program. At the beginning, of course, it will be difficult, very difficult. But with time, you will have lectures on quantum computing, lectures on neuromorphic, and the von Neumann architecture will be out. You have to learn about that. Of course, we need a lot of time to convince people to do quantum computing classroom or neuromorphic computing. We need some time, but the future will be there.
Okay, thank you so much.
Good day. I'm a PhD student from this faculty, Hubert-Zuzowski, and I'm working on materialistic optimization. And thank you for a great presentation. This topic certainly seems like a future, or at least a part of it. And when you talked about the inspiration from brain, I wondered, like many times, even in specifically in materialistics, researchers are inspired by some part of biology, although it turns out that their algorithms don't necessarily mimic their biology. It's just their perceived description of what is actually done in biology. And here, this architecture mimics human brain. But seems to me, I'm not a neuroscientist, that there maybe are some important differences, like two things I thought about during the presentation, and I think maybe you explained how they are addressed, but I would like to delve deeper into them. So first, the human brain is changing. Like we get new synapses, and the reinforcement learning is ongoing in us. So when I make a mistake, my hardware changes. And as you said here, the software is really close to hardware. And you said previously that there are some hardware architectures that can readjust. So is there more to it? How do they? So because when you think about a chip, it's, it's photogenically pre-made. So how do you learn with your already implemented solution?
I forget to mention one important keyword, self-adaptation and adaptive behavior. This is very important, even in optimization problem. If you have dynamic problem, if you have a noisy problem, if you have important. Okay, so your question is, of course, you have thousands of neuroscientists working on how the brain is working. So we have a lot of knowledge. We have a lot of knowledge. And those people, as I show you, for instance, implementing the neural model, what is the architecture of the brain, what are the different type of neurons. Even me, I cannot, at least in the 2 years or the 3 years, I cannot implement all the knowledge of neuroscientists. There is a huge bridge, what we are doing and the knowledge in neuroscience. The knowledge in neuroscience is much, much more important than that. But you have to trust those people. And we have new technologies. Just 2 weeks ago, I went to a neuroscience seminar. There is a new technology of imaging. They can see the architecture of the brain at the neural level now. There is new technology in imaging, etc., etc. So, one information, the knowledge in neuroscience is huge. And we need 10 years minimum to include all this knowledge. Whose knowledge? If you would like to have details about the different type of neuron, different part of your brain, believe me, you need a lot of time. So, what we are doing, this is why, I told you, this is why I switched from lava to Nengu. to reuse the knowledge in neuroscience more quickly. I'm reading papers in neuroscience about reinforcement learning, etc. And the model is already implemented in Nango. Knowledge is here, and don't have doubt about that. And knowledge is evolving a lot. We have new technologies to have more information about the brain. And we have the chance to have those simulations. They have been designed by neuroscientists. I'm reusing them quickly. So this is one of the reasons that I switched to Nango, because with time, my objective is to be more biologically plausible. I start with an objective, proof of concept. With this engineer, proof of concept, it works with very simple ideas. But now our objective is include more knowledge from the brain, and of course, include what it works in optimization. And to try to have the best mapping. At the end, I'm here to solve problem, good quality of solution, good latency, and energy consumption. And the proof it works, your brain it works. So the best proof is your brain. Okay?
Okay, thank you.
But the knowledge in neuroscience is huge. People are working more than 1 century, and they have new technology to have more information about the brain. So we are using less than 1% of the knowledge. We are far, far, far from neuroscience. If you just would like to have the different type of neurons, 1 month of reading. There is not one type of neurons. There are 100 types of different neurons, architectures, hierarchy, fractals, everything is there. It's very complex. I'm not here to say that we will have the most, exactly the perfect brain model, but go towards.
I have another question. It's about the encoding. On one slide, you presented various types of encoding that you use in neuromorphic computing. But I can imagine some more types. For example, the value of the action potential or the amplitude of a spike could be an information that is passed through the system. And as far as I believe that you know that in the human brain, or in the biological brain, it's the chemical potential. But if in neuromorphic system, those are electromagnetic signal, we can also think about we can encode the information in the frequency, amplitude, and the phase. So, do you use some other type of encodings, or just those two that you show are the only ones that you can use, and why?
This is a good question. This is a continuation of your question. The information encoding is one of the open questions in neuroscience. This is it's a huge word, okay? But what we know, for sure that some part of the brain we have rate encoding. What we know, in some part of the brain we have time encoding. We have burst coding that combine rate and frequency. This is for sure. We have some knowledge, but still some questions are open. Come on, this is for sure. So, I have the same answer here. The literature related to information encoding is huge and is open. Everything is not closed questions. So we start by using. I have used only rate, simple rate, and time encoding. I didn't use population, burst, mixed, etc. We have, as I told you, in binary problems, the encoding is not straightforward, okay? But if you have mixed problems, if you have continuous problems, if you have permutation problems, the encoding question will be more complex. But what I did in solving, for instance, the traveling salesman, we have used time encoding. time, I show you this. I skipped this slide, excuse me. But for instance, in traveling salesman problem, you show the architecture I used. We have excitatory neurons. We have inhibitory neurons. And we use time encoding and inhibition between neurons. Every column here will implement one city. So if this column is city 1, I have to send a signal to other neurons to block them to be 1, because it's permutation. So the exercise of information encoding for solving a problem, it's a huge question. Just for traveling salesman, I had to design a new architecture for representing permutation and to satisfy the constraint of the permutation. So I have used two types, what we call the winner-take-all. This is one known architecture in neuromorphic. It's if one neuron is excited here, all those neurons must be inhibited. If not, you don't have permutation. For me, information encoding is the most important because it will influence the search space, the search operators, etc., etc. This is the beginning of the story. There are 10 people or 5 people working on this in the world. We need some time.
Thank you. Do we have some questions still?
Okay, but what architectures, feed-forward or recurrent, are more popular nowadays or useful maybe?
The architecture will be heterogeneous, hierarchical, because you have one part which encode the search space, one part which encode the objective function, one part which encode the selection, etc. So for me, the architecture will be hierarchical, heterogeneous, and you have to design it manually.
Yeah, and test.
Like in artificial network, you have different layers, convolution, etc. You have to design it manually. But what we would like to do is how to do it in generic way, the most generic way possible. But currently, I do it manually.
Okay, thank you.
Okay, other questions? Maybe some other participants.
I forget to mention something. No one asked this question. One of the disadvantages of neuromorphic computing is the precision. We have 8-digit precision, no more. So you cannot have floating points. Everything is not perfect, but your brain is also low precision. And even in artificial networks, the low precision training, what we call, I forget the name, using reduced precision for the weight, quantization. So here quantization is natural. In Louis, I have 8-digit precision. I cannot have more, so I have in the encoding, if you would like to handle high precision, you have to solve the issue.
Okay, do we have questions from here, or maybe somebody participating online would like to ask a question? If no, maybe the final matter from me. In the world of quantum computing, we have the situation just like here in neuromorphic computing that there are lots of simulation software and some hardware. Yes, of course, they are developed somehow. Yes, and recently, I don't know, maybe 2 months ago, I was in Wrocław. This is one of the also quite old Polish city, and they have Wrocław University of Technology. We have good contacts. They have actually bought this low temperature quantum computer. It has 5 qubits. Yes. And they can solve the traveling salesman problem on the size of 3 right now. Yes,
I know that.
My question is, when we'll be able to put on our desk or maybe in our computing center a reliable yes, maybe not quantum, we can see that it's far to go, yes, but maybe this neuromorphic computer, and we won't pay a fortune for it, and it will be able to solve something more than three cities,
Thanks for this
TSP.
question. You know, 5 years ago, 6 years ago, I have even some papers trying to use the quantum encoding, you know, but by simulation, how to encode solution using quantum representation, etc. Forget about that. So 5 years ago, everyone in operation research community, optimization, everyone now is working on quantum, you know, it's like a new... 5 years ago, I start to think about this. One internship, and we start at the end, we solve the knapsack. We cannot solve the knapsack more than 10 objects. And I stop doing research in this area. And the second motivation, when I saw the number of, in our community, the number of people that switch to quantum optimization, quantum machine learning. Okay, good. And then I read a paper 1 year ago from physics, ERC project, one ERC project from physics, far from computer science, that make a parallel between quantum and neuromorphic in terms of material devices, photonic, etc., etc. And I asked myself, let's have a look. So I start to have more knowledge about quantum. I will tell you, I was disappointed when I see the noise in the press and the reality. No. There is something strange. A lot of money. The money is infinite, you know. And when I see the results, and I was very pessimistic for my generation to see quantum computer that solve real problems. So until now, you have to know that there is no success story that quantum is better than digital. Until now. And it will not be for tomorrow. 10 years, 20 years minimum. I think that the noise on quantum and the result, there is some gap. There is some gap. I was disappointed, really. Yeah? I think that neuromorphic is more realistic than quantum because quantum, there are huge problems. I don't know if you are familiar with problems in quantum. To design a quantum computer, there are huge problems of noise. And I will add something. Energy consumption. No one is talking about that. You know what is the energy consumption of quantum computer? Did you see quantum computer? The space they are using and the energy they are using cryogenic to reduce the noise of the quantum. The energy used by the quantum, no one is talking about. The cost, no one is talking about. I think, of course, quantum physics is important contribution in solving optimization problems, combinatorial optimization problems. Okay, but there is a gap today between solving real problems and the quantum computers we have. To switch from 5 qubits to 10 qubits, you need 2 years, 3 years of work and a lot of money. So be careful. We need to keep ourselves realistic and modest. I think quantum computing is still a lot of work, Huge problems, correcting errors, scalability, energy consumption, huge work still to do. I don't think that my generation, I will see quantum computers solve efficient problems better than digital. From my generation, I don't think so.
Okay, thank you very much for sharing your thoughts and a great presentation with us. Thank you, everybody, for participating. And let me already invite you to the second meeting in the beginning of December. We'll have Gabriela Ochoa, who is co-organizer of GECO conference. And now let's thank again Professor Talbi for today. Thank you.